Okay, so I've decided that we're just going to go right back into our paper. This paper is actually really, really long, and we've made some pretty good progress, right? We are finally at the end of, we're at the end of the spacetime algebra section, and we're about to do this section right here, section 3.71, the Spinor Representation. So with that, let's begin. All right, so here we are about to study this notion of Spinor representation. We've just gotten off the idea of figuring out how to rotate, right? We're rotating general bivectors in the spacetime algebra, and then we learned how to apply this to any vector any multivector in the spacetime algebra. So we had this object here that we converted into this double-sided product. And we now write that as U as RF, R reverse. And that is how we create the rotated version of F, right? And very convenient. We've worked through that whole thing and we learned how to do it. Now we are going to move into a section what we call Spinor representations. Spinors we learned from quantum mechanics as a mathematical object to represent states of spin 1/2 in elementary non-relativistic quantum mechanics. And a representation is a matrix, is a collection of matrices that mimic some that mimic the behavior of a group or a vector space or anything that you're representing. If you take some algebraic object like a group or a vector space or a ring, and you replace the algebraic elements with matrices, and matrix multiplication mimics that group, that's a representation of the group. So we're trying to figure out somehow we're going to use spinors to represent something in our space-time algebra system. So that's what we're expecting to learn here. So let's begin reading. Recall that in equation 3.57, we converted the exponentiated commutator bracket into a double-sided product, right? I just showed you that, didn't I? That was this whole thing right here. Exponentiated commutator bracket is right here. There's the commutator bracket. And notice this was just on the left side, but we converted it to this thing. We did actually quite a long... I spent quite a bit of time demonstrating why this was the case. But this becomes a two-sided product of regular exponentials. And this is the form we use to represent the rotation of F. We never use this form. We use this form all the time. That's what they're saying here. Since such a double-sided product is a more natural algebraic representation of a group transformation that can be extended from bivectors to the entire algebra. So it's an algebraic representation. So using the bivectors, that in itself is it's a way of representing the group, which is the Lorentz group, right? That's the one we're talking about. And the Lorentz group is a transformation. Each element of that group is a transformation that will transform our multivectors. And so we're using the algebra, the space-time algebra. We have pieces in it that represent those transformations. That's what these U's are. These exponentiated forms of sigma 3 and sigma 1 and sigma 2, those are elements of the space-time algebra, right? Just to be a reminder, of course, it's minus sine alpha over 2 sigma 3, and then it's cosine alpha over 2 minus sine alpha over 2 sigma 3, right? That is what this thing is, right? And this is just a real number, and this is a bivector. Boom, it's inside the algebra. So we have an algebraic representation of the Lorentz group transformation, because that's what this is. This is a rotation in the Lorentz group, or a boost, I should say. So specifically, if we notate product factors like this, then the transformation has this form, which we just went through, where we have used sigma 3 reversion as minus sigma 3. Now, to make sure that we understand and remind ourselves how that works, it's just, you've got to remember, sometimes we're thinking in the full four-dimensional space-time algebra with gamma mu, and sometimes we're thinking in the three-dimensional geometric algebra with sigma I, right? But sigma I, regardless, even if we're thinking here, sigma I is understood to be a bivector, right? And the reversion of a bivector of sigma 3, so sigma 3 is actually gamma 3, 0, and gamma 3, 0 reverse, so sigma 3 reversion is gamma 0, 3, but that equals minus gamma 3, 0, and which equals minus sigma 3. So sigma 3 reversion is minus sigma 3, right? So, you've got to be a little flexible because sometimes it's very nice to think of just terms of 3D geometric algebra where these guys are the basis vectors, where sigma I are the basis vectors. And that's great, but every now and then you've got to remember, no, these sigma I's are actually bivectors. And then they just point out that these factors satisfy the normalization condition. Hence, this form of the transformation makes it clear how the transformation preserves the product structure of the algebra. So in order to be a representation of the algebra, that's really the key. Every algebra has a product, and the product structure of the algebra has to be preserved in matrix terms. But in this case, we're using the algebraic representation, where U represents these transformations. So the product structure of the algebra is represented by this, right? You take two multivectors, G times H, the product, G, which is the geometric product of G and H. But UU reversion is 1, so you can slap it right in the middle, and then you can take the whole thing and put it on the outer ends. And that looks like UG, U reverse, UH, U reverse, which looks like the transformations of G and H, which this is just, that this becomes G prime, and this becomes H prime, right? Which is the same as GH prime, which is what this is. So you can multiply, so you could multiply and then transform, and you'll get the same thing as if you transform and then multiply. And that's what we mean by preserves the product structure. Then they remind us we call the quantity U a rotor to emphasize that Lorentz transformations have the geometric form of a rotation through spacetime. And we studied that a lot in our last two lessons. Just remembering that rotation has to be understood in a rather general way to include boosts, which are these hyperbolic rotations, right? Specifically, the rotation generators, S and K, the rotation generators square to -1 and produce spatial rotations, while the boost generators, K, square to +1. So here I'll just remind you that this idea here, first of all, we know that the boosts are produced by our relative vectors in the spacetime algebra. So sigma 1, sigma 2, and sigma 3 produce the boosts. And that's gamma 1, 0, gamma 2, 0, gamma 3, 0. The rotations are generated by these S's. Now, S, remember, I squared equals 1, right? The pseudovector, the basis of the pseudovectors squared is -1. So I inverse is just minus I. So you have I times minus I equals 1. So I inverse is minus I. So what you want to write is you want to write SI equals minus sigma I. But they don't like to use that minus sign in front, so they end up writing sigma I inverse. That's why you have this inverse right here, right up here. You have this inverse because they don't want to put the minus sign out front. But let me flash back and remind you that these were the commutation relations that ended up looking just like the Lorentz group, right? But in order for this to be the case, S1, gamma 2, 3, S2, gamma 3, 1, S3, gamma 1, 2. In order to get these guys from our sigmas, which is sigma 1 is gamma 1, 0, well, I guess I'll go sigma k is gamma k0, right? In order to do that, you have to define sk is sigma k I inverse, right? That's how it's done. So just, these are little conventions we have to keep in mind. Okay, so specifically the rotation generators square root of -1, while the boost generators square root of +1 and produce hyperbolic rotations in spacetime. Since the rotor representation of a Lorentz transformation produces a geometrically meaningful rotation, the bivector f can be replaced in 360 with any geometric object that can be rotated. Indeed, any multivector M can be Lorentz transformed according to mu inverse. Now, if you go back to where we studied rotors and rotations, we proved this. We proved that any multivector M can be Lorentz transformed or rotated according to this prescription, right? So this is not something that you need to infer based on geometrically meaningful rotation. I don't think, it's not clear to me why, because this is a geometrically meaningful thing, therefore you can replace this with any multivector. Any geometric object can be rotated. That's like English, that's not math. But we did do that, and we did prove that before in a previous lesson. The rotor U is an example of a spinor psi, which is an element of the even-graded subalgebra of the spacetime algebra that may be decomposed as psi equals zeta plus f, where zeta is a complex scalar and f is a bivector. Okay, so this is where we start getting a little heavy, right? A rotor is an example of a spinor psi, right? And what they're saying is, I guess what they're saying now is psi is defined because it says psi, comma, which is an element of the even-graded subalgebra of the spacetime algebra. Now, if you looked at this, you might think, wow, that doesn't look like the whole even subalgebra, right? Because that's a scalar, that's a bivector, but the even subalgebra should also include pseudoscalars, right? So, because pseudoscalar, that's grade 4, that's grade 2, and that's grade 0. So that's the even subalgebra. And that's confused me for a while, but of course I wasn't reading clearly because zeta is a real number plus the pseudoscalar, right? It is a complex scalar. So you can see how this notation can really get out of hand if you're not careful. If you don't realize that psi is a complex scalar in this prescription, you're wondering where is the pseudo vector that is supposed to be part of the even graded subalgebra. So anyway, but this is the even graded subalgebra, and what they're saying is a spinor is some element of the even graded subalgebra. Now, what you and I know spinors are totally different. We know spinors are as two-dimensional, well, as column vectors of 2D complex column vector, right? That's a spinor, and it's got its row vector counterpart. So evidently, there's some correspondence between these things, right? But as far as this paper is concerned, all we need to know is that a spinor is an element of an even-graded subalgebra. So the obvious question is, what is this connection? Because they don't talk about column vectors anywhere around here. So let's read on just a little more. This even-graded subalgebra is closed under the full Clifford product, meaning you take the geometric product of any two even-graded elements of the algebra, even-graded multivectors, or multivectors which do not have vectors or trivectors, where I could write trivectors as a vector times the pseudovector. So if you do take any geometric product of multivectors that only have even-grade components, you'll always end up with another multivector with just even-graded components. As an example of this decomposition, the boost rotor, this is a boost rotor can be expanded in terms of hyperbolic trigonometric functions as this. Now, we've done tons of that in our last lection, which is the sum of a scalar and a bivector. Similarly, the spatial rotor can be expanded in terms of circular trigonometric functions. Okay, so why is that an example? That's an example of a decomposition of the even graded subalgebra. So I guess what they're saying here is that if you have a rotor U, it's definitely in this even graded subalgebra, and therefore, by definition, it is a spinor, because a spinor is by definition an element of the even graded subalgebra. So we know that our rotors clearly have real parts and bivector parts, real part and bivector parts. Okay, but look, I want to know what this connection is between a spinor and this even graded subalgebra. And so that is our next subject of diversion, because if you read the rest of this paragraph, it doesn't really bubble up. And now all of a sudden we've got this word spinor floating around. We need to understand the connection. What is the connection between this, and is that relevant to quantum mechanics? Turns out the answer is yes. So now we're going to take a diversion and sort of understand the connection between this and spinors that we have always known about from quantum mechanics. Okay, one moment, please. All right, so to make this connection as best as I can, let's go back to our elementary quantum mechanics, and we're just going to talk about spinors. So this is the spinor. This would be just the spinor part of a wave function. So we're ignoring any spatial part in the momentum space or in regular space. We're just going to look at pure spinors. If you do a lot of quantum computation, this is all you do. You only think of qubits in terms of pure two-level spinors, right? Qubits are a very popular subject now. You know, everything's talking about the Bloch sphere. This is all about the Bloch sphere. But we can just take it to its bare bones, right? Where we're looking at a quantum mechanical state is just broken down into two parts. It's a superposition of the 0 state and the 1 state, the lower state and the upper state. And the superposition has two complex numbers, alpha and beta. These are complex numbers now, right? And so this is sort of the bracket notation, very typical, used in this subject, a sort of two-level system subject. But we can also create this spinor object, which is a column vector with alpha and beta in the two positions. Now this thing has 4 degrees of freedom, the real part of alpha, the real part of beta, and the complex part of alpha and the complex part of beta. So it's two-dimensional in the sense of complex numbers, but it's 4 real numbers. So that is how you write down a spinor in elementary quantum mechanics. Now, also in elementary quantum mechanics, you have the observables, the operators, the spin operators. And almost always, these are these 3 Pauli operators. Sigma 3, which we put first because it's the diagonal. We choose sigma 3 to be the diagonalized operator, and sigma 2 and sigma 1 are not diagonal, right? They have this form. And actually, this is kind of the interesting. This is one of the things that geometric algebra promises to deal with is, well, look at this. You've got these eyes here, right? You know, quantum mechanics, this is all pretty arbitrary, it seems like what is this eye all about? And the math all works out. It's all very tight when you get your head around the whole thing. But the promise of geometric algebra is to sort of explain these eyes in terms of geometry, which is interesting. But right now we're just reviewing the basic quantum mechanics. So we've got these 3 Pauli matrices, which are essentially all of the spin operators can be constructed from these Pauli matrices, and then you have the spinor itself, which really represents the wave function of the atom or the molecule or whatever qubit you're working with. So I'll write down qubit. That's not standard quantum mechanics language, right? That's the language of the subject of quantum computation. But nowadays, more people know about qubits than they do about two-level systems, right? Which is, or spin 1/2 systems. And I'm serious about that, right? Qubits, people don't necessarily talk about spin 1/2 when they study qubits in quantum computation at all. They don't care. They completely abstractify what these two states could be. But when I look at this, I think immediately of just, an electron with spin 1/2. What else could it be? I mean, that's the most archetype, that's the basic system that you would consider here. These are angular momentum operators, and these, this would be SX, or SZ, SY, and SX. The actual spin operators, there's a factor of Planck's constant over 2 that will probably, I can't remember if I put it in here eventually or not. But the point is this is the spinor, right? This guy here, and these matrices are the representations of the angular momentum. Anyway, so if I want to find, for a given spinor, if I want to find the expectation value of sigma 3, I literally am going to do a matrix process. And that matrix process is going to look like alpha conjugate, beta conjugate, 1 minus 1, and alpha, beta, right? And if you execute this multiplication, you should get this expression, this number. I used a different, when I drew this up, I used a different form for the conjugate. So the conjugate's actually like that. And you end up with this expression, right? And same thing with sigma 2. If I want to find the expectation value of sigma 2, I throw in here the matrix sigma 2, which has that minus sign, these off-diagonal terms, and the little i's, and you end up with this expression, alpha beta conjugate minus alpha conjugate beta, all times I. And likewise for sigma 1, I get alpha beta conjugate beta, right? So this is how you would calculate these expectation values using the regular spinor algebra. So let's see if we can connect this. I want to connect this ultimately to the geometric algebra. So now we take a look at these things here, and we say, well, this is the expectation value of an angular momentum in each of these directions. Now, what we're going to do is we're going to give each of these a name. We're going to call this N3, N2, and N1. And we're going to kind of imagine an angular momentum vector where the components of the vector in three-dimensional space are these three numbers right here. And if we did that, the magnitude of this vector, right, would be basically the magnitude squared would be the sum of the squares of these three objects. So let's square these three objects, add it together, and find the magnitude of this titular pseudo-angular momentum vector. I'm nervous about calling it an actual angular momentum vector, of course, because the Pauli exclusion principle. Not the Pauli exclusion principle, but just the Heisenberg uncertain. No, which one? Just the principle of complementarity, that you can't measure all these things at once, but you can still speculate about this vector, right? This is ultimately related to the notion of the block sphere. But what we're going to do is we're going to write down this number right here by squaring each of these terms and adding them together. So when we do this process, we take this first one here and we square it to get these three terms, right? And the second one, when we square n2, this I squared becomes a minus 1 out in front. But the inside is just easy to square. But the interesting thing is this will cancel with this, right? You'll get a cancellation right here when you add them together. This will cancel with that. So that's good. And then when you take the third term, which is this guy, and you square it, you get these three terms. Now here you get cancellations here with those two. So the only surviving terms are this term, and this term. And when you take the survivors down and write them out together, you realize that that is just AA conjugate plus BB conjugate squared, which is psi against psi squared, which is 1. So the point is this magnitude n squared is going to equal 1. And that tells us that we can take this magnitude n and we can create this notion of a block sphere of radius 1. And this arrow is going to, or the arrow representing n is going to have two coordinates, coordinate theta and a coordinate phi. So it'll only have two coordinates. It's going to be pointing somewhere on this sphere. It's a vector in space, right, with magnitude 1. So it must have only 2 degrees of freedom, and we can just represent it as an arrow pointing on a sphere, and that's typically called the block sphere, right? Another very well-known concept from quantum information science. Okay, so with that idea that we're taking these 3 expectation values and throwing it onto a block sphere with 2 coordinates, now we have to kind of worry about, now what we're going to do is we're going to work on these 2 coordinates to identify this vector n, which represents these expectation values. So here's my little picture of things. Let's see if I can label it well, right? This angle here will be the angle theta. It'll be the, I guess we would call that the polar angle. And then this would be the azimuthal angle right here. So that's the polar angle. The projection of, and this of course is the vector n. The projection of n on the, this would be the x3 axis. That projection would be, of course, cosine theta. And then the projection, actually this kind of looks a little skewed, doesn't it? Yeah, I think this red line here, in order to actually kind of do my projective geometry, right, should look something like that, right? Yeah, that's better. So cosine theta, and then cosine theta doesn't really look as good there as it should look. It should be here. Let me see, hold on. It should be here, cosine theta, and it should represent this distance, right? And likewise, these projections here are going to be, in this case, this particular projection is going to be cosine theta or cosine phi, right? That's this projection. And then this projection here should be cosine theta. Wait. Not cosine, it should be sine theta cosine phi, right? Sine theta, right? Because this distance here is sine theta. So it should be sine theta cosine phi. And this part here will be sine theta sine phi. Okay, that'll be this distance here. Okay, so we can break n up. This is our vector n. We can break this guy up into these component parts, right? I've done that. Where did I do that? I did that right here. So we're going to say that the n3 component, which is that the component along the 3-axis, that's just going to be cosine theta, right? But we know what n3 is. It's these two. It's this product of the complex numbers and their conjugates subtracted from each other. So that we're going to call alpha squared and beta squared, because alpha conjugate is just sort of alpha squared, beta squared. And what we're going to realize is cosine of theta has to equal the difference of 2 squares. But we know what that is from trigonometric considerations. We know the double angle formula. I think it comes from the double angle formula. So it goes cosine 2 theta equals cosine squared theta minus sine squared theta. So what we're doing is we're sort of turning this into some kind of reverse half angle thing by replacing 2 theta with theta and theta with theta over 2, right? So we can replace alpha and beta with cosine squared theta over 2 minus sine squared theta over 2. So that's exactly what we do. So we assign alpha the value of cos theta over 2 and beta the sine theta over 2. Now already you see these half angles coming in, which are exactly what we get in our rotor form. So we're kind of leaning already into the rotor form. The problem is that when you take a complex number and multiply by its conjugate, if there's an overall phase, you can't really detect it if all you're looking at is these two real numbers. So we have to include an overall phase as a possible part of alpha. So alpha ultimately, it's proportional to cosine theta over 2, but there's another phase factor in here that'll disappear when you take this conjugation. Same with beta, and those phase factors are obviously independent. So now we're going to replace alpha everywhere we see alpha with cosine theta over 2 e to the I gamma and sine theta over 2 e to the I delta. So then we just go to n1, which we know is alpha beta conjugate plus beta alpha conjugate. But we know what alpha and beta are. They have these real parts, which are going to come out front, and it's going to leave behind just these phase pieces, which I've organized to be gamma minus delta. So the phase of alpha minus the phase of beta is the form. So gamma minus delta is sort of its own factor now. But you see I've done it in order to be constructive here, right? Because I have e to the I some phase plus e to the minus I some phase. And if I just throw that with a 2 over 2, you can see that this piece right here is going to look like a cosine of gamma minus delta, right? So that's good. And then I do this for n2 as well, right? Same thing, but now we have this I out there. And what are we going to see? Well, we're going to see the same thing, the cosine, half angle cosine and half angle sine. But we also have now the difference between these exponentials, which is going to, and then there's this I up front. And so this is going to be I times the sine of these two things. So I now redefine the difference between these two phases as phi, right? And then I say, okay, our ket, psi, which we are expressing in the representation of a spinor representation, which is this two-dimensional thing. We now have something we can put in these spinor slots. This is alpha, and that is beta. And now I can take alpha and beta, and I can multiply both. I can multiply the whole spinor by e to the I gamma, where I end up getting this difference down here in this denominator, or not denominator, in the lower part of the spinor, right? So you see this gamma minus delta. Well, here I have delta minus gamma. And then I can keep working this to extract a gamma minus delta from everything. So now I have the gamma minus delta in both components of the spinor, and of course it ends up being multiplied by gamma plus delta on the outside. So now this is beginning to look, because you know I'm about to replace this with phi, and sure enough I get cosine theta over 2 e to the I phi over 2, because that's going to be phi, and then e to the minus I phi over 2. And then I ignore this, because now this is a global phase of the entire spinor, and we ignore those global phases, right? So we are left with a spinor that is modeled like this. And that is exactly how we model things on the Bloch sphere, right? This is quantum mechanics, right? This is actually familiar to those of us who've done quantum mechanics. And even those who have worked quantum information science, you actually derive this thing. So now, what have we done? We've basically we've done no geometric algebra, right? We've just taken this and we've created this sort of Bloch sphere spinor form that encapsulates all of that information. So I guess it's worth taking a moment to understand how we interpret this. So if we have, let's say we started with a vector n on this block sphere, right? It's block sphere because n has always got unit length, right? So we know theta and we know phi because that's how we know n, right? So I can write down, I can calculate cosine of theta over 2 and sine of theta over 2, and I can calculate these two numbers as well, and I'd end up with a complex number here, but I'd end up with a version of, this would be alpha real plus I alpha imaginary, and beta, the real part, plus I beta, the imaginary part, right? And those imaginary parts come from the I that lives in here, where this gets replaced by cosine phi over 2 minus I sine phi over 2, for example, right? That comes in here, right? And so you end up, when you multiply everything together, you end up with a real part and an imaginary part. So you can calculate all of these numbers using these formulas, or using the formula for the spinor that we just figured out. And this situation on the block sphere, this particular value of n, if that was the state of our two-level system, and I chose to measure the angular momentum, or I measure the state of the system in the basis x3, the probability of finding it is going to be, or finding it in the state 0 will be related to this length. And if my basis was in x, I guess x1, it would be related to this length, and x2, the probability would be related to that length. So that is basically the quick and dirty analysis of the block sphere. Now we need to somehow connect this to geometric algebra. So let's first take note that we still have these coordinates that we've laid out. Now notice that this is not symmetrical, right? N3 has a certain kind of favoritism in the terms of simplicity, right? This is nice and easy. In order to write this expression down, we have to choose sort of an axis to measure these coordinates off of. So this breaks sort of the mathematical symmetry in the sense that not all directions are easy to calculate, but it doesn't break any significant symmetry because this is generally true regardless of what axes you choose. So there will be this interesting asymmetry will emerge in our calculations, and it all can be traced to choosing these three axes. But say you've chosen those axes. So now, once I've chosen those axes, I can actually write them down in a sort of a vector form, right? I can say, well, this is the x-axis, so I'll call that sine theta. This is the component on the x-axis. So sine theta, cosine theta, sigma 1 will be the basis vector in the x direction. And 2, sine theta, sine phi will be the basis vector in the y direction. This is sine theta, cosine phi in the x direction, sine theta, sine phi in the y direction, and then just cosine theta in the z direction. Now you should see where this is going, right? These are just basis vectors sort of on our block sphere, right? This would be the sigma 3, sigma 1, sigma 2. Let me see, no, this would be sigma 1, I think. But regardless, you have the three basis vectors. Those are going to be what jumps into our geometric algebra. These are going to be bivectors in the space-time algebra, or they're going to be regular vectors if we're looking at this in terms of the three-dimensional geometric algebra that is embedded in the space-time algebra, right? Whether they're the relative vectors or whether we think of them as bivectors. But we'll think of them as the relative vectors for now. But then I can take this structure here and I can actually break apart the inside by pulling out this sine theta, right? And what's left behind is cosine phi sigma 1, sine phi sigma 2. And then, of course, cosine theta sigma 3 is left over here. But what I should recognize right away is that this piece here is actually the rotation of sigma 1 around the sigma 3 axis right, which would be in the plane, well, the rotation of sigma 1 about the sigma 3 axis, which, and it's a spatial rotation of sigma 1 about the sigma 3 axis. And recognizing that, I can write that down as sigma 1 rotated around sigma 3 using our prescription for rotors, right? So this is the rotor, this is the reversion of the rotor. I want to move it an angle of psi, right? No, phi. So I write it as phi over 2 here, but that rotates it by, when I use this prescription, that rotates it by a full angle of phi. So just to, I don't know, drive it home again, if this is a rotation, let's execute it, right? So this exponential can be broken down using Euler's rule this way. I sigma 3, because remember, we're rotating around the axis sigma 3. We recognize this as rotation around the axis sigma 3. So that means we have to rotate in the plane of sigma 1, 2, which is I sigma 3. That's where these I's are coming from in this. I guess to be clear, that's not standard in the rotors, right? Rotors have bivectors up here. And here we have a bivector times okay, so I guess if we're looking at in terms of the space-time algebra, right, we have a bivector, which is this relative vector, times the pseudoscalar times the grade 4 pseudoscalar. So a bivector times a pseudoscalar, this should be another bivector, right? But if we look at it in terms of the 3D geometric algebra that's embedded, right, then we think of this as a one-dimensional vector, and this is now a three-dimensional or grade 3 pseudoscalar. I shouldn't say one-dimensional. I say a grade 1 vector, a regular vector, and this is a grade 3 pseudoscalar, which would be written as sigma 1, sigma 2, sigma 3. It turns out, you look carefully at all this, I'll just remind you, it's all equivalent, right? It has to match because remember that three-dimensional geometric algebra is embedded in the space-time algebra. But that's why you see this I sigma 3 here, is we're thinking about rotation around the axis sigma 3. But remember, all rotors really refer to a plane of rotation. So you've got to get this I in there. Okay, so that, and there you see, here we have our I sigma 1, sigma 2. This minus sign comes down here. The sigma 1 drops down here like that without much trouble. And then likewise, this rotor using its Euler form becomes this thing right here. Notice sine sigma over 2, sine of psi, I keep saying psi, it's phi, sine of phi over 2 is a real number. So whether it's on the left or the right of sigma 1, 2 is irrelevant. So the fact that I've got it on different sides here doesn't matter. But this expression here is this rotor, is this, not the rotor, it's the rotation of sigma 1 in the plane, which caught our eye when we noticed that when we wrote down the full vector form of our block vector, we noticed this little embedded rotation. So we're kind of flushing it out. So if you take this and you finish all the multiplication, you multiply sigma 1 to the left, you get cosine phi over 2 sigma 1, and then you change this to a plus sign because you're going to exchange sigma 2 and sigma 1, and they're orthogonal, and they anti-commute, so you pick up a minus sign when you do that flip, but then psi 1 geometric product psi 1 is just 1, so that's what that comes from. And then you have this product to execute, and this is just cosine phi over 2 sigma 1, cosine phi over 2 sine phi over 2 sigma 2, plus this cross term. You have these two cross terms, and then you have sine squared. The two cross terms, how did we do this? Oh yeah, we just jump into trigonometric relationships, right? The cosine squared and the sine squared of phi over 2 together. Wait, there's a minus sign missing here, right? Because the cosine squared phi over 2 plus sine squared phi over 2, that would just be 1. You need the difference between these two to end up with this double angle formula that we used earlier. But these two, I think, do work out to be sine phi. Let me find out where my minus 1 went. Oh, okay, I think I found it. When I multiply this term by this term, right, you end up with a sigma 2, sigma 1, sigma 2, right? And then you have to flip these two to get minus sigma 1, sigma 2, sigma 2, which equals minus sigma 1, right? So this here should be a minus sign, right? And now you have cosine squared phi over 2 minus sine squared phi over 2. And that combines to give cosine of phi. And then this one and this one combine together to give you sine of phi. Okay. The point being is that this final result here is actually what we had here. So it just shows that this is in fact the rotation, and this rotation does in fact get you this thing. That was just a long demonstration to show how that worked. Okay, so now that I believe that this is given by this rotor form, right, where we're taking this vector and we're just rotating it, I can now make the replacement, just straight make that replacement. You know, I'm replacing this with its rotor form right here. And I replaced I sigma 3 with sigma 1, sigma 2, just to make it very clear. And what do I do next? Then I pull out this exponential, this rotor. I pull out the rotor. Now it's easy to pull it out to the left because sine theta is a number. So I can just move that number in and it just sits right inside. The question is, what about pulling it out to the right? Because what I've actually done is I've kind of taken this and thrown it inside here. So it's almost like I've pulled it all the way out. And how can we do that? Well, what you have to realize is that sigma 3 commutes with sigma 1, sigma 2, right? If you flip sigma 3 through, you get pick up a minus sign, then another minus sign. So sigma 3 commutes with sigma 1, 2. So that's another way of saying rotating in this plane doesn't affect sigma 3. So because of that, the two exponentials that sandwich cosine theta sigma 3, this guy is going to commute through. It will not pick up a minus sign, and it will cancel with this, and you'll end up with cosine theta sigma 3. So I can put it in there, and if I expand this out, I get sine theta sigma 1 sandwiched between the rotor and its reverse. But when I get cosine theta sigma 3, it's also sandwiched between the rotor and the reverse, but it commutes with the reversion, and then the two rotors cancel out, and you're just left with this term. So this is one of those maneuvers where it kind of is elegant in geometric algebra, because I'm using the geometric algebra rules here. But is it all that easy to see that? I mean, it takes these little extra insights to simplify stuff in geometric algebra that you have to kind of know. You have to be pretty familiar with this. It's a new way of, you have to understand everything that commutes with everything. And you have to keep that in the front of your mind to simplify this stuff. And so I think proponents of geometric algebra just like to show, oh, look how easy this all is. It all comes together. But, you know, if you have to work through each and every step in your little mind, you have to track different things than you're used to tracking. And I can't say that those things are harder to track. It's like learning a new language, right? Because, you know, it's still mathematically clear, but instead of just immediately realizing that things can be distributed, you have to realize that, oh, this commutes, therefore I can distribute it. So that's just a personal reflection on that. But nevertheless, here we are. And now, once I'm in here, I realize I'm in the same situation as I was back here when I realized that this was a rotation. Now I realize that this is a rotation, and it's a rotation of sigma 3 in the plane of sigma 3, 1, which is about the axis of sigma 2. Right, so now I can introduce, and I won't go through all the math like I did before because it's the same thing. But now we have this. I wrote this down as like the rotor is this, but that's not true. The rotor, well, okay, it is true. The rotor here is e to the minus sigma 3 sigma 1 theta over 2. And now if I take these two together, right, these two together, the actual rotor for the whole thing is this expression here, right? And so I can now write the vector n, right? I'm realizing, remember where we started, right? We started, this is the vector n, right? This is n as a vector. I call it the block vector from two-level system language, right? And quantum information science language too now, I guess. And so all of this is just rewriting the vector n. So when I'm all done, the vector n is just this rotor, and here's phi, and here's theta, right? So those two numbers that define n are actually embedded in this rotor, and now n is just sigma 3 rotated with this rotor, right? So I've now written n using the geometric algebra language, right? It's still a vector, right? It still comes out to be this guy right here, which is still derived from this, which is derived from, these quantum mechanical calculations, right? So, but it's now using geometric algebra of rotors to define n. So that's pretty cool, I guess. So our last step is to compare this rotor R, which basically has all of the information for the spinor n. Remember, this sigma 3 is an artifact of the fact that sigma 3 shows up there is not particular to this block vector n, right? All the information about n is contained in phi and theta, right? This sigma 3 is there because of sort of the asymmetric mathematics of choosing the polar coordinates that define sine theta. So this is a formula for n, and sigma 3 belongs in there all the time as sigma 3. So now we need to take this rotor n and connect it up to the literal spinor that we're so familiar with from the block sphere. And so we can kind of do that, right? Because we know that this part represents the I sigma 2, right? Sigma 3, 1 is I sigma 2, sigma 1, 2 is I sigma 3, and sigma 1, 2, sigma 3, 1 is I sigma 1 when you work all that out. So these coefficients that exist in front of these bivector terms can be matched with the expansion of this block vector. And if we expand this block vector into its real and complex parts, we get these four real numbers: cosine theta over 2, cosine phi over 2, cosine theta over 2, sine phi over 2, and these pairs down below. So what we see is that this A0 term, which I'll call A0, not alpha 0, but A0, cosine phi over 2, cosine theta over 2, that can be found right here, and we will call that A0 also. So those match. And then we see, okay, let's look for the I sigma 1 term, which would represent a rotation around the sigma 1 axis. sine phi over 2, sine theta over 2. Well, here's sine phi over 2, and here's sine theta over 2. But there's a factor of I here. So this guy we're going to call, we'll call this A1, and we'll call this I A1. And then we'll look at this term here. We have minus cosine phi over 2 sine theta over 2. Well, here we have cosine phi over 2 sine theta over 2, but without a minus sign. So we'll call this, just the real number part, right? We'll call this with a minus sign. We'll call that A2, and then we'll have to call this minus A2, right? And then the last piece we have to match up is the dual of sigma 3, and that's sine phi over 2 cosine theta over 2 with a minus sign. Well, here we have the minus sign, but we don't have I. So if I call this A3, then I will call this IA3. And then in the end, of course, this is what the final spinor looks like. So now, I'm good, because if I start with a spinor, here, just give me an arbitrary spinor from quantum mechanics, it's a legit spinor. So I have a real part, an imaginary part, a real part, an imaginary part. I can break up these real and imaginary parts, and I can plant them in this expression, right, with the real part, or the grade 0 part, and this is the grade 2 part, and I look for the number. I take this one here and I put it in front of the I sigma 1. I take this number here and I put it in front of, I figure out what A2 is, so I take the opposite of the number that's living in that. I take opposite of the real part of the second component, and I call that A2, and I put that right here in front of sigma 3, sigma 1. And, I do it for all three. And now I have taken an arbitrary spinor. This was my goal, right? I've taken an arbitrary spinor and I've converted it to a rotor, which is, in fact, an element of the even subalgebra of the spacetime algebra, which is the whole thing I was trying to show. So that is the connection between spinors in quantum mechanics and even subalgebra elements. And in fact, it's a little more specific. It's not only just part of this connection isn't just the even subalgebra as a whole, because you don't see any grade 4 parts in this, right? So it goes to just a real part and a bivector, and furthermore, it's actually going to be a rotor. So spinors in quantum mechanics translate into these rotors in the geometric algebra. And just to put a fine point on it, if I take the spinor 1, 0, right? Well, I go with my prescription. A0 is 1, and all three of these guys are 0. So if I put in 1 for this value, right? That becomes A0. These guys go away, and what I'm left with is the prescription for that rotor is the rotor is now 1. So the block vector is going to be represented in the algebra as 1 sigma 3, 1 reversion, which is just sigma 3. But notice that this step is sort of superfluous almost. It's the 1 that matters the most, right? Because all the information is contained in the 1. Likewise, if I wanted the down spinor, well, the down spinor, I have to go back to this, and I say, well, now I have this slot is held by minus 1, right, is the real part of this. This is minus 1. This spot is held by 1, right, because this is 0, that is 0, so the whole top is 0, that's 0, so the imaginary part is 0, but this is 1, so minus A2 equals 1, so A2 equals minus 1, right? So if A2 equals minus 1, then you have minus I sigma 2. And so what I'm expecting is R R is going to be, this is minus I sigma 2 is the spinor. And if I calculate minus I sigma 2, I get sigma 1, sigma 3. So I have now sigma 1, sigma 3, sigma 3, sigma 3, sigma 1, which is the reversion. These two guys disappear to 1, so I have sigma 1, sigma 3, sigma 1. That ends up being minus sigma 3, which is sort of the opposite of this. So now this represents the block vector in the geometric algebra. I guess I should make this an arrow, right, like that, because it's not really equal. Now the question is how do we find expectation values and other things in the geometric algebra? And we're not going to go into that. But I have shown the connection which answers this question back here, right, about spinors being elements of the even-graded subalgebra of the spacetime algebra. So that's the whole point of what we're trying to do today. Okay, so it's a pretty long lecture to get to there, but it does make this connection, and so now we can move on. So I'll see you next time.